Okay, to explore another type of exponential function, let's consider a hypothetical example where you wanted to start a deer ranch. And you put deer, a couple deer in the ranch, maybe 4, 6, I don't know how many deer you have. In fact, we could start with a number. I didn't put that up here. Let's say you wanted to start with, let's go with 10. You put 10 deer in the ranch, right? Start with 10 deer. It's always good to have a starting point. Let's say you start with 10 deer and you find out over time, you kind of address this and count the number of deer. And over a 5-year period, the number of deer triples. Okay, so in other words, year 0, you put 10 deer into the ranch. 5 years later, you got 30 deer. 5 years later, right, that'd be tripling. 5 years later, you get 90 deer. 5 years later, you get 270 deer, and so forth. Well, eventually, there's going to be too many deer for the land, right? So it's going to eventually level off. But let's consider the fact that maybe you have an ever-growing ranch, and you're able to house an indefinite number of deer on this ranch. Then you can model the growth of the population using an exponential model or an exponential equation. Let's look at how this would work. Let's just take some data. Okay, so let's look at a table. We'll set this up with number of years. Actually, let's not go with number of years. Let's go with the number of 5-year periods. Okay, number of 5-year periods. That's going to be my first row of the table. Then we're going to have in here the number of deer. We'll start it this way and then we'll maybe adjust for the actual number of years. Okay, so number of 5-year periods. At period number 0, you'd start off with 10 deer. After that point, after 5 years, which is the first period, the first 5-year period, you'd have 30 deer, it triples. Then after the next 5-year period, you would have 90 deer. After the next 5-year period, you would have 270 deer. After the next 5-year period, you would have what's triple of 270? 810. You'd have 810 deer, and so forth, right? This table goes on indefinitely. Again, assuming your ranch can house that many deer. Okay. And again, this is a hypothetical example. I'm not saying that deer populations actually triple every 5 years. This is just making the numbers work out well. Okay, so now let's look at a model that would represent this. To get from one input value to the next, you're adding 1 each time, right? You're adding 1, adding 1. This is the number of 5-year periods, okay? Well, in the output, you're multiplying by 3 each time, and so forth down the line, okay? So, if you think of the number of 5-year periods as your x value, and the number of deer as your y value, then you would start, the y values will start at 10, and then, well actually we'll construct the formula here, but if you think about it, you start at 10, then the next value is 10 multiplied by 3, then the next value is that previous amount multiplied by another 3, and then here you start at 10 multiplied by 3, by 3, and by 3, and then here you start at 10 and multiply by 3, by 3, by 3, by 3. So you're just adding an extra factor of 3 each time down the line, each 5-year period, okay? And then, when you calculate each of these, you'll get the value in the table. As you notice, as you go along, the number of the period, the 5-year period, will correspond to the number of 3's in the value, right? The 4th period is 10 times 4 3's. And so you're going to get a representation in shorthand where the number of 3's can be represented as an exponential. 3 squared, 3 to the third, 3 to the fourth, and so on. And it's the power that represents the number of 5-year periods, okay? So you start with a 10, and then you multiply by 3 raised to the power of x, whatever x is, because x is your number of 5-year periods, okay? This model, this equation, will give me any number of deer after any number of 5-year periods. If I wanted to figure out, say, the number of deer after 7 5-year periods, well, the number of deer after 7 5-year periods would be equal to y equals 10 times 3 to the 7th. Now this you might need a calculator for. I'm not even sure what it is, but it's a relatively large number, okay? Okay, so actually let's go ahead and calculate what that is. So I'll grab my calculator here. I do 10 times 3 raised to the 7th power. You get 21,870. So you'd have 21,870 deer on this ranch after 7 5-year periods. Well, of course, that's 35 years down the road, okay? That's a lot of deer, okay? But you can see the model kind of develop out of this repeated multiplication by this main base of 3, okay? You have your starting point, which is also very important because that shows up in the model as well. So there's 2 key features here, 2 key numbers. The first one is the coefficient, or the multiplier here, which is 10. That, of course, gives you your initial starting point. And the 3, which is the base on your exponential part, that is going to be the factor by which you multiply each time you move to a new period. Of course, another very important feature is that the variable is in the exponent because it's the number of factors of 3 that changes each time, okay? Now, a very important aspect here is that when this base is greater than 1, like the number 3 here, you're going to get a growth. It's going to result in a growing value as you move down the line, okay? So as a general principle then, if I think about the structure of an exponential function or exponential model as y equals c times a to the x, as we've seen now with exponential decay, if that a value is now greater than 1, you get a growth, you get an increase in those values, okay? So when a is greater than 1, you get a growth. Okay, we call that exponential growth. Now, what does that look like graphically? Okay. Well, I might need some more space here. Okay. What I could do is just start plotting these ordered pairs. If I were to have 0, 10, let's put 10 way down here. Actually, let's get up to 800 maybe, a little over that. I'll put 800 on the graph here. Then 400 is half that high. 600 is in between. I'm just going to get a few, nice markings in here. Maybe I'll get every 100 in here. And then we can figure out the rest. Just kind of estimating. Okay, so there's up to 800, a little bit of buffer there. And then going out to the right, we'll go out to 4. 2, 3, 1. So at 0, 10, I have a point. That's pretty low on the graph there. 1, 30, that's also still pretty low on the graph. It's about a third of the way up to 100. 2, 90, well, we're almost to 100 now. 3, 270. 3, put it around there. Oops. Let's kind of make that a little bit more horizontal. There we go. And then let's go 4, 8, 10. Somewhere up there. And so you can see how this graph really grows quickly. And if I were to go to the next level, you know, even up to 7, this graph would be up to 20, almost 22,000. So, I mean, it's just growing like crazy at that point. Okay, so you can see it kind of starts off slowly, even though really you look at this tripling, it's still not really a slow increase, right? It seems like a big increase, but when comparing to, you know, what it is later on, it starts out relatively slow and then really increases in its rate of growth later on. Okay. Now, I'd like to connect these because, again, at any point in between, you could still have a population, right? At 1.5 years, you'll get a population that's somewhere in between 30 and 90. I'm sorry, 1.5 periods. Right, so if you were 7 years out, for instance, or 8 years out, you're kind of between that first period and that second period. And so you get an output somewhere between 30 and 90 in theory. And so you could have any number of points in here, data points, but they would eventually all kind of link together with this curve. Now what's interesting is if I were to extend this back to the left. Now, of course, I don't have data points for anything before that initial input of 10 deer. But if you imagine going back a period 5 years ago, before I put the deer in, what would have happened? What would I have needed to get? What would I have needed to put in order to get to 10? Well, it's 1/3 of that 10. Well, so it'd be what? 1/3 of 10. 10/3 is 3 1/3. Is that right? Yeah, 3.3. So you'd have to go back, you'd have to divide by 3 to go back. And so what you end up with, if you continue to divide by 3 to go backwards, right? To go right, you can multiply by 3, to go left, you divide by 3. Continually dividing this number by 3 will always result in a positive value, right? You start at 10, divide by 3, divide by 3. It's always a positive divided by a positive. So you're always going to have a positive value, but it's going to get smaller and smaller and smaller. It's going to really get close to that x-axis, but it's never going to hit at the x-axis because it's never going to hit 0. It's got to stay positive. And so what you'll end up with is an asymptote, which I can't even really draw. I'm drawing it very wobbly. Somehow I've got to get an asymptote in here, but again, to get the idea, that's not too bad. You can almost tell there's a difference there. So there's an asymptote, it's getting very, very close to the x-axis. Okay. So with an exponential growth, in theory, now this is just kind of a cool model, but mathematically speaking, if I plug in, negative values for my input, -1 for instance, that's just 10 times 3 to the -1, or 10 to the 10 times 1/3. If I did 10 times 3 to the -2, that's 10 times 1/9, and so forth. And you end up, the denominator grows, which gets this number smaller and smaller. Okay? Okay, so just some general principles. Now, I could have changed my inputs from the number of 5-year periods to the actual number of years, right? That would have worked also if I had done X is number of years and Y is number of deer. It does change the model slightly. This one was 10 times 3 to the X, just so I have a reference. What we end up with is a table that would have 0, 5, 10, 15, 20, and so forth, and then, but the same outputs. And so to turn these years into 5-year periods, you'd have to divide each one by 5, right? 10 divided by 5 is 2, 15 divided by 5 is 3, and so forth. So if x is the number of years, or actually, you know what, let's change it to t. I like t for time, right? Time in years. Then you would have a model that's y equals 10 times 3 to the t over 5. You're dividing these t values by 5 to get the number of periods. So it just kind of changes the exponent slightly. Actually, what it does is it then gives a vertical, what was it? No, a horizontal, thinking about if you change the variable, remember this is our transformation stuff. If you change the variable from x to x over 5 or t over 5, whatever, that's going to be your horizontal stretch actually, right? Yeah, horizontal compression is greater than 1, horizontal stretch is less than 1. So if you're multiplying by 1/5, you stretch it out horizontally. So anyway, that's a transformation of the graph. Now, a couple other features of an exponential growth, the domain and the range. Let's take a look at those for a moment. In fact, I'm going to go ahead and erase this hypothetical situation. Let's just look at the idea of an exponential in general. C times a to the x. Now again, we said if a, this base, is between 0 and 1, then there is exponential decay. That's a decrease. And if a is greater than 1, then there is exponential growth. Now, each of these situations have their own properties. First of all, both of them will have all real number domain. Obviously, you can plug in negatives, you can plug in positives, you can plug in decimals, fractions, whatever. You can always plug stuff into an exponent and calculate what that value is. So we would say that the domains of each are all real numbers. So here, the domain is all real numbers, and here, the domain is all real numbers. The range, we just saw on this one, the range had to be positive. Remember, I said you take 10, you divide by 3, you divide by 3, you divide by 3, you're always getting a positive number. If you multiply by 3, you always get a positive number. So the range, or the outputs, those are positive numbers, 0 to infinity. You can't ever hit 0 because division by 3 never results in 0. And also we saw with the exponential decay, you can also never hit 0 there. Okay, so the range is still positive, or all values greater than 0. With the exponential decay, we saw that it was a decreasing function, okay, and it was 1 to 1, so it's decreasing. We know that it is a 1 to 1 function, and it has a horizontal asymptote at the positive x-axis. The positive side of the x-axis. Whereas with an exponential growth, it's going to be an increasing function. It is also 1 to 1, passes the horizontal line test. So it's increasing. It's 1 to 1. And its horizontal asymptote is at the negative x-axis. Okay. Also, in both cases, the y-intercept is going to be the c value. It's what you get when you plug in an x value of 0. Okay, so in both cases, the y-intercept is at 0, comma c, and here also the y-intercept is at 0, comma c. All right, so that c value is always the y-intercept. Okay, so it gives you kind of a breakdown of all the things that, all the different features of the graph, main features of the graph and the properties of the function. Another thing that's important, you'll see a couple other interesting points on these graphs. The value, if I plug in a 1, you get c times a to the 1. If you plug in -1, it's c divided by a. So there's a couple kind of interesting points at 1 unit over and one in each direction. So on here you would have, well, I guess in both of them, the points 1, comma ca is on the graph, and -1, comma c over a is on the graph. Okay, so that's true for both of these. So just a couple other little features that are interesting.